All right, good morning, everybody. Welcome back. Um, I think we're going to talk about the U substitution today. Just before I get started, I promised you last time that I was going to record and post the videos on our on YouTube, but last time I recorded it, but then I realized my microphone was off in my recording, so I didn't get any sound. So um, last time's class will not be posted. Sorry about that. But I'm all better now, and everything's going to be great from now on. So sorry about that. I assume it doesn't really matter. But all right, let's get down to it then. We're going to talk about the U substitution. This is something that apparently you guys said you saw a little bit of in your last class. So you know, whether that's true or not, I'll assume you haven't seen any, but hopefully you have seen a little bit. So at the end last time, I wrote up some formula. Now this, I'm going to write it again. This formula is not really worth memorizing per se, because when I do the U substitution, I don't really think it through in this way. But let's just talk about what sort of our interpretation of this formula should be. Sorry, I left out a dx on the left side. There's not enough room. Can I try something here? That's not what I wanted. That's all right. Dx should be right there. I'm not accustomed to moving stuff around in my erase. Come on. All right. Okay, it's perfect. So what I see on the left side is, when you see this, what you see is g of x inside f of x, right? And then this right here is the derivative of that inside part. All right. So when you look at this formula, and really, like I said, I wouldn't suggest you try to memorize this formula, but what you should remember is, on the left side, what I want to see is a thing on the inside of f followed by the derivative of that same thing. So when we have on the left side, what we have is f with stuff inside, followed by, or I'll say more specifically, times the derivative of the inside stuff. All right. If you can see that inside the integral, then it will simplify to the right-hand side. And what is the right-hand side? The right-hand side is just the integral of f. All right, which is simpler. You don't have to think about the inside anymore. On the right-hand side, you don't see that function g of x anymore. It's just turned into some new variable u. So the slogan is, if you can see f has some stuff on the inside, and then it is multiplied by the derivative of that same stuff from the inside, then you can turn it into just the integral of f, which is in general a lot simpler. That's the idea, is to make the integral simpler. So as a kind of procedure, how do we actually do this? What you have to do is you have to look at your integral and identify something on the inside of something else. And so you look at the integral, you find something, I will say, inside. Now there's no like hard and fast rule for this. You have to sort of get a feel for it, and sometimes you have to improvise a little bit. But inside could mean something inside of parentheses. It might mean inside of a square root sign, or inside of an exponent, or inside of another function, something plugged inside of a trig function or something. You gotta be a little creative sometimes in looking at your formula and trying to judge something which is inside of something else. All right, and then you call the inside thing u. So the u is what appears on the right side of this formula over here. And when you're actually doing this procedure, the substitution, the way you want to do it is you find this thing on the inside and you call that u, because that's what goes inside of the f on the right side of the formula here. All right, you call that u. Then find the derivative of u, because that's what we want to see next in our formula is f with something inside of it, and then immediately followed by the derivative of the thing on the inside. Now I called the thing on the inside u, so I find the derivative of u and call this du. And let me just say, as a technicality, this will become clearer in a moment, that du always includes dx. All right. You'll see what I mean by that in a moment. And then, anyway, what we do is now you try to substitute to use only u's and du's in the integral. All right. And then you can finally, once you've substituted away all the x's, you change everything into u's, then you can just do the integral. And hopefully at that point the integral will be simpler to do. This is the general procedure. So I'll say then do the integral. Once you've changed all the x's into u's stuff, then you can do the integral without any trouble. So let's try a simple example, and then we're going to do some, less simple examples. Any questions so far? This is the general procedure. I think it may not make much sense when I just write down the words. Let's just try an example. How about integral 2x times x squared plus 10 to the power 6 dx. All right. Maybe I should have said as like a step 0, very preliminary step is see if you can do the integral without doing the substitution, because it's always easier if you can already do the integral. And on the homeworks usually it's clear just because of which section the problems are in, but maybe on a test or something I'm not always going to say like, hey, by the way, for this one you have to do the substitution, or for this one you don't need the substitution. It's a good idea to look at it and just ask yourself, can I do this by some other means? In this example, you cannot do this by some other means because, well, you have a multiplication right here, which is always a problem inside of an integral. You could try to do away with that multiplication by distributing or something, but you cannot distribute inside of a 6th power like this. You could try to actually do the 6th power, but this is possible, but I would say you don't want to spend your evening doing that, right? Doing the 6th power, this would be like doing the FOIL thing 6 times, which nobody actually wants to do. So you should feel like there is no really good alternative. Let's do the substitution. So we begin by choosing a part of this to become the u, and I'm going to write it right over here. Any thoughts about this? What do you think? You want to pick out something which is on the inside of something to be the u. Yeah, how about x squared plus 10? That is inside the parentheses. Always a good idea. X squared plus 10. Great. Okay, now the next step I said was find the derivative of u and call it du, so I'm going to do that right here. Du is the derivative. It's 2x dx. This is what I meant when I said the du always includes the dx. In order to make the trick work, when you find the du, which is the derivative of u, you always multiply by dx at the end. You could imagine that this is kind of like the chain rule. You're taking the derivative of x squared is 2x and then times the derivative of x squared. But you don't have to think about it in that way. All right, anyway, now we are, so I just did this step here. Find the derivative of u, call it du. Du always includes dx. Okay, now substitute to use only u's and du's in the integral. So I go back to this integral here, and I'm going to try to replace everything that you see there in terms of x with something in terms of u. So the first thing I can do, once you get used to this, you can probably do all of this in your head at once, but I'm going to just try and break it out into a few steps. First, I'm going to just plug the u in exactly where it is. So this right here is the u, x squared plus 10. So I'm going to leave everything like it is, except put the u like it is, right? Instead of x squared plus 10, I put in u. This you can always do without really thinking about it. You just put the u where it goes. All right, and now the question is, what is all the stuff which is left over, and how am I going to express the leftover stuff in terms of u's and du's. Now, if you're lucky, the leftover stuff just straight up equals the du, and that is actually what happens here. You can rearrange this a little bit just to make it even a little clearer. I just changed the ordering, right? U to the 6 times 2x dx. Like I said, if you know what you're doing, you can skip these intermediate steps. But anyway, the reason I wrote that is because this 2x dx is the same as du. So in fact, this is just integral u to the 6 du. And I have completed the substitution. All right, we have replaced all the stuff which was in terms of x with the appropriate stuff in terms of u's and du's. Not quite done yet, but are there any questions about what I did so far? Like I said, if you have done this before, you probably can skip some of those intermediate steps, and that's fine with me. All right. In this example, we got a little bit lucky just because of these red underlines here. They ended up matching exactly. That doesn't always happen, and sometimes you have to do an extra little step in the middle there, but we got lucky this time. I'm trying to do an easy one. Anyway, just to finish off, you need to actually do the integral. I hope that you wrote this integral sign every time in those intermediate steps because I haven't done the integral yet. The integral is when you actually do the antiderivative. I'm going to do it right now. The integral of u to the 6 is 1/7 u to the 7 plus c. So at that point, you do the antiderivative. The du disappears. That's because the d whatever always goes away when you do an integral. You don't write the integral sign anymore, and you don't write the d whatever it is. And then you insert the plus c. That's because I just did the indefinite integral. We're basically done. There's one final step that you always do at the very end, and it's always easy, and that is you replace the u with x's again. Because the original antiderivative was a function in terms of x, your answer should also be a function in terms of x. You don't want to give a function in terms of some new variable u. So my final step is just to replace, instead of u, I replace it with x squared plus 10 because that's what u is in terms of x. So it is 1/7 x squared plus 10 to the 7 plus c. And this is the end of the U substitution. Any questions about all that? This was an easy one. I hope it makes sense. Hope it seems familiar from your youth.
So I don't know if you can see this on my screen right now, but how I wrote it equal to the integral, is that how you want it presented on tests, homework, that kind of stuff?
Hold on a second. I'm trying to see your screen. Equals, sure, yeah, that's fine. Yeah, I mean, or you could write it, you can just get down to this end here is the answer, so you don't have to restate the whole thing if you don't want to. Yeah, great. Okay, one cute thing about the U substitution, it can be kind of difficult. Like I said, this was sort of an easy one, but one thing you can always do with these is check your answer at the end. Anybody done this before? You remember how could I check that this is the correct answer?
Do the derivative, right?
Yeah, you can take the derivative of your answer. The whole point of this procedure is that this thing that I ended up with is supposed to be the antiderivative of what I started with. That means if I did it right, the derivative of this will equal this thing that we started with originally. So we can check it. Check yourself before you wreck yourself. You take the derivative of the answer, 1/7 x squared plus 10 to the 7 plus c. And this is a good idea to do if you have, a few extra minutes on the test or whatever. What do we do for this derivative? Well, first of all, the plus c is going to go away when I take the derivative of that because the derivative of a constant is 0. And then the derivative of this part, I do the chain rule. The 7 exponent will come down in front, so it'll be 1/7 times 7 x squared plus 10 to the 6. And then when I'm doing the chain rule, I got to multiply times the derivative of the inside, which is 2x. And this, if you simplify, those 7's will cancel. This is x squared plus 10 to the 6 times 2x. And that really is the thing that we started with on the inside, isn't it? It's in a different order, but it is the same. So what you're trying to see is that this and this are the same. The same. So that means it's right. All right. Or it means you made some very coincidental mistakes in both parts and it ended up matching when it's not really. That doesn't often happen. All right. Any thoughts about that? This was, like I said, a fairly easy example of the U substitution. All right, let's try a few more that are less easy. I got a few more examples that I want to do, and then I have some for you to try. See how you feel. Let's try this one. Integral x squared square root 1 minus x cubed dx. All right. How you like this one? What do you think? What should I choose to be the u? Somebody shout it out who hasn't shouted yet today.
All right, I already went, but I'll take the u on this one. It's going to be 1 minus x to the third.
Okay, yeah. That is the inside of something. Like I said, you want to choose the inside of parentheses or a square root sign or an exponent or something. Great. And then the du. Someone tell me the du. Somebody else?
3x squared.
3x squared, yeah. You wanna add anything to that?
Plus c.
No.
dx.
dx, yeah. This is something that a lot of people forget, and to be honest, it doesn't really matter most of the time if you forget to put the dx there, but sometimes it can be confusing if you leave it out. So I always try to put it in there. As I said last time, if you learned a slightly different way of doing this substitution, that's totally fine with me. As long as, however you want to do it, it's fine as long as you are doing it a correct way. You don't have to write it exactly the same way I do. Okay, anyway, let's begin the substitution. I start plugging stuff in like I did last time. I'm going to begin by just sticking the u where it goes in the formula. So it's x squared and then square root of u dx. If you're used to this, like I said, you can probably skip some of these steps. And then I find it is good to kind of separate out the u parts from the x parts to see like what is left over here. And the way that I like to do that is I'll just write the u stuff first. This is just rearranging the things inside the integral. I sort of shove the u stuff over to the left and then push the rest of the stuff over to the right. So the stuff which remains on the right is what I have to deal with. X squared times dx. What am I going to do about x squared times dx? Now, in the previous example, when I got to this point, this thing actually equaled du. But in this case, it does not equal du. This is x squared dx. This is 3x squared dx. Almost the same, but the 3 messes it up. And so the extra little step you got to do here is the old divide the constant trick. This you have to do in most examples. Usually this thing does not match exactly. Now there's a couple different ways that people learn to do this, but the way that I do it is I'm just going to divide this 3x squared dx. Divide the 3 onto the other side there. So du is 3x squared dx. Dividing 3 onto the other side means 1/3 du is x squared dx. And now that does match what I have inside the integral, x squared dx. And so this is square root of u times 1/3 du. That dividing the constant was just to make it so that the thing I had matches the du. All right. Sometimes when people learn this, they sort of down inside the integral, they multiply by 1/3 and also multiply by 3. If you want to do it that way, that's fine with me. If you don't know what that is, that's also fine with me. All right, we have now replaced all the x's with u's. There are no x's remaining in the integral, which means we're ready to do the antiderivative. One simple thing before that is I have a constant multiple on the inside of the integral sign. You should always factor that out to the front. Remember, this is a rule about the integral. You can move a constant multiple out to the front of the integral. If you leave it on the inside, it might end up confusing you about what to do with it. You don't have to do anything with it when you take the antiderivative. All right, now we are ready to do the integral. How do you handle the square root sign in an integral? Do you remember how to do that?
Raise it to the 1/2, then u.
Yeah, right. So you should just rewrite this. Actually, this is almost always what you should do in a calculus class. It is almost never helpful to write a square root sign as a square root sign. You should interpret the square root sign as a 1/2 power. And now it's clear how to do the antiderivative. The 1/3 stays like it is outside, And then for the exponent, I increase the exponent by 1. So 1/2 becomes 3/2. And then I divide by the exponent like that. 1/3/2 u to the 3/2 plus c. All right, and then the final step, which is always easy, you replace the u with whatever it is in terms of x. So my final answer is 1/3 times 1/3/2. Would you mind if I say 2/3? I don't like fractions inside of fractions, although I don't really care. I mean, you can write it however you want. But okay, I replace, instead of u equals 1 minus x cubed. So 1 minus x cubed to the 3/2 plus c. And there you go. This is my answer. If you want to, you can check the answer by taking the derivative. I don't need to do that. I'm confident. And you all would tell me if I did it wrong, I think. Any questions about that one? Excellent. Okay, let's do, I got a few more examples. I said I had some for you to try. I don't know. Well, yeah, we got plenty of time. Okay, let's try one which has boundary values. This is a definite integral. All right. How do we handle a definite integral? Again, there are two ways that people typically learn how to do this. I'm going to do it one way. I'll mention the other way, but you, as always, you can do it however way you like. The way that I like to do a problem like this is do the antiderivative first, just like we did in all those other examples. Then plug the values at the very end. The values, I mean the 1 and the 4. All right. This is how I'm always going to do these. If you want to do it some other way, that's fine with me. So do the antiderivative first. What I mean is, just for now, and for most of the problem, I'm going to ignore those two values, the 1 and the 4. I'm just going to do this just the same way that I did all of those other examples. This is actually pretty similar to the other examples, so I'm going to choose the u to be the inside of the parentheses. I hope you were expecting that. And then the du, what do you think? I can see all your names on the Zoom here. I'm going to shout out. I hope you don't mind if I get aggressive with the name calling. How about Julian? Can you tell me what the du is?
6x dx.
Excellent. 6x dx. Great. Okay. Now, because I know the future here, I'm going to divide the constant here. You basically always have to do this, dividing the constant, in order to make the du match up with what you end up with. Okay. Great. Let's try and plug this stuff in. So this integral now becomes integral. First, I put the u where it goes. So it's x and then u to the 10 dx. Like I said, I'm going to write all these intermediate steps, but if you know what you're doing, you can probably do several of these steps in your head. So I have u to the 10, and then what's left over is x times dx. But because I've already worked out the du and I divided by the constant, x times dx is 1/6 du. So this is integral u to the 10 times 1/6 du. I've completed the substitution. It's all used now. Now I can factor the 1/6 out of the integral, because I always am going to pull out a constant if I can. U to the 10 du. All right. All right. We can next do the antiderivative. What do you say, Gabriella? Please tell me if you go by a different name or something. Yes, so we got the 1/6 outside, and then the integral becomes 1/11 u to the 11. And then, so I'm going to say, at this point, remember, I've been forgetting about those boundary values here. Ordinarily, at this point, I would put a plus c, but I'm just going to say no plus c, since it's a definite integral. Actually, if you put the plus c, it won't matter. If you do everything properly, the plus c's will cancel and you'll get no c in the answer anyway. But if you can just remember, when you're doing a definite integral, you don't have to put the plus c at this point. Okay, and the very last step is to replace the u with the x's. So this is 1, would you mind if I say 1 over 66? I usually don't simplify, but I happen to be an expert at multiplying 11 by a single digit. 3x squared plus 5 to the power 11. All right. I have done the entire antiderivative, and now at the very end, I said my strategy was do the antiderivative first and then plug the values at the very end. So right here, I'm going to go the bar and plug in the 1 and the 4. All right. The whole time you do everything exactly the same. You just at the very end, instead of putting the plus c, you plug the values in. One thing you have to remember is to complete the substitution and put the x's back at the end. You don't want to plug these numbers in, the 4 and the 1, for u at this point, because those numbers, the 4 and the 1, refer to values of x, not values of u. Now, the other way that you may have learned to do this is somewhere in the middle, you translate these x values into u values. You have to do an extra little step, and that's fine if you want to do it that way too. Anyway, we are pretty much done here. I get 1 over 66, 3 times 4 squared plus 5 to the 11, minus 1 over 66, 3 times 1 squared plus 5 to the 11. And that's my final answer. This is how I would leave the answer, you know, on a quiz or a test or something. If you want, on your homework, you can plug it into your calculator, but even that, I don't care if you plug it into your calculator. All right, any questions about that one? This was another U substitution. Okay, I have one more example of this type. They don't get much harder than this, except for, actually they do, but I have one more example of the not so difficult ones. I just thought it'd be a good idea if we do one with a trig function in it. So how about sine x over cosine to the 4x dx? This is going to be great. Now this one perhaps immediately is a little puzzling because I don't see any parentheses or square root signs or something like that. So maybe it's a little less obvious what the u should be. Anybody have any ideas about this? Or maybe you do see parentheses that are kind of hidden. Sometimes that can happen.
Is it the cosine of x?
Yeah, cosine to the 4 of x. You have to remember what that means. This is very strange, in my opinion, that anybody even writes things like this, but it's a common thing in when you're working with trig functions. Really, what cosine to the 4 means, it means this. This is what I was trying to refer to when I said maybe there's some sort of hidden parentheses. Cosine to the 4x really means cosine of x to the power 4. And now maybe it's a little clearer what we should choose to be the inside of something. We're going to choose u to be cosine x. You might be a little worried about what's going to happen with the sine x. Well, we'll see. We'll work it out. What's a du going to be in that case? Anybody know how to keep it straight?
It's negative sine.
Negative sine of x. Yeah, the derivative of cosine is negative sine x. dx, of course, always goes as part of the du. All right. Now maybe you should feel a little bit better about the sine x. I don't know if you were worried about what's going to happen with the sine x. Actually, now you can see the sine x is going to end up being part of the du, so it'll be great. Let's try to plug stuff in then. So, as usual, I'm going to just plug the u where it goes, first of all. Sine x over u to the 4 dx. And now I like to try and sort of separate out the u parts from the x parts. In a fraction, the way you got to do that is something like this. I'm just going to sort of split the fraction apart into its denominator times its numerator. All right. And now it becomes clear what you have to do. You got to match up this sine x dx with the du. Now they're almost the same, but that minus sign is a little troublesome. So you're going to divide the minus sign over to the other side, just like dividing ordinary constants. Like so, right? Sine x dx is negative du. So This is integral 1 over u to the 4 times minus du. And as always, I factor constants out. That negative sign inside the integral can be pulled all the way out to the front. Integral 1 over u to the 4 du. And now my substitution is complete. All right. I hope you kept straight the cosines and sines. It's easy to mess up the negative signs there. Anybody want to suggest what should my strategy be when I do the integral of 1 over u to the 4? How do we handle 1 over u to the 4?
Put it to the negative 1.
Yeah, it's a negative power. So I'm going to write, instead of 1 over u to the 4, I'm going to write it like u to the minus 4, right? And then this we can easily do the usual thing with the exponent. You increase the exponent by 1. So I have the minus sign out front. And then I'm going to increase the exponent by 1. It is negative 4. You increase, it becomes negative 3. So 1 over negative 3 u to the negative 3. And I put the plus c at that point because it's the antiderivative. All right. And then my final step, plug the x's back in for u. So u is cosine x. So finally, those minus signs will go away, right? 1/3 cosine x to the minus 3. And I'm going to leave it at that. If you want, you can write that cosine in a denominator again to the 3rd power, but I don't care about that. Negative exponent in the answer is fine by me. All right. Any thoughts about that one? Not all that different from the others.
So then we don't have a negative to the power. Could you put it like over 1 instead?
Yeah, sure, if you want. So it would look like 1/3, 1 over. You can even do it like that if you really want. I know some people don't like negative exponents.
I think can't you just do like 1 over 3 cosine to the 3rd x plus c?
Yeah, if you want. Yeah, these fractions will multiply.
Okay. Yeah,
Yep.
perfect.
Sure. Yeah, anything like that would be acceptable to me. I find it easier to just leave it like this. Although, depending on your upbringing, I know some people have like some sort of biological compulsion to simplify things in certain ways. And if you want to do that, that's totally fine with me. I sort of leave it as it lies. Once I'm done doing the integral, I drop the mic. But you can do whatever you want. All right. Excellent. So I got one more, which is actually harder. So these ones, all of these are sort of more or less routine. If you have the procedure down, you do the same procedure every time, and it works out. This last one that I want to do is an example where it can be a little trickier. Check it out. If you did this in high school, I don't know. I remember doing the substitution when I was in high school. I was not like a math superstar when I was in high school, but I did take a calculus class. But we never did one like this. This one they didn't show me how to do this one in high school. This is a pro strategy here. What should concern you when you look at this? If you are going to do the substitution, you will notice I have the thing on the inside. The natural choice for u here is x plus 1. But the problem is the du in that case would just be 1 dx. And then I'll have this extra x hanging out. What am I going to do with this extra x? That's the problem. But anyway, in fact, so I'm going to say my strategy here is, this isn't much of a strategy. You may need extra tricks. And this can be tricky. From example to example, you may have to kind of improvise a little bit to make it work. But I mean, they're all kind of similar. Anyway, what we're going to do in this case is you still choose the u to be the inside. So that's not the issue. Actually, now if you were following along the other examples, you might feel like this is going to be a bad choice because you have the extra x. But stay with me here. The du is just 1 dx, right? The derivative of x is 1. And so when I plug this stuff in here, it's x and then square root of u dx. Now the square root, of course, I'm going to write as a 1/2 power. But then what's left over, and this is the real problem, what's left over is x dx. This does not match the du, and you can't make it match by dividing a constant because you don't have an x in here. That's the real issue. Anybody seen one like this before? Or anybody have a fancy idea about this? Yeah, what do you think?
Yeah, I think you can take the outside x instead of taking the inside x plus 1. Like, so then you use, like, your u equals is x, and then your du is, like, the square root of x plus 1.
That actually, I think, will not work. Although this is a good idea. You know, sometimes you just make a bad choice of the u. If I were to do that, I'm gonna do this. If I were to choose u equals x, then du is dx. And
sorry,
so
dv. Since I'm using like the integral formula, or like the integral of u dv. Like I learned that in high
okay.
school.
Yeah, so that's another trick which we're gonna do later on. That's called the integration
Yeah, so
by
then you
parts.
use each of the one. So like one's the actual u, and then one's d of v. So like then it's two separate.
Right. I think that also will not work in this case, but I don't want to do that in any case because that's something else that we're going to talk about later on, if you don't mind. You're using some fancy tricks from the future, which I don't want to get into. You can actually do this with the ordinary U substitution. Anybody have an idea? That was a good idea, by the way, but it's from the future. Check it out. Here's the extra trick. This x, this is not part of du. That was the problem, right? But it can be written. I'm stuck on the side of this line here. I don't like this line. In terms of u, check it out. U equals x plus 1, which means x equals u minus 1. This is the trick. If you have extra x's hanging out, which you can't realize as part of the du, sometimes you can realize them as actually part of the u, not part of the du. So this x here, I am going to replace with u minus 1. So this becomes integral u to the 1/2 u minus 1 dx. What am I doing with the dx? Well, dx actually equals du in this case, right? It says up at the top there, du equals 1 dx. So this is integral u to the 1/2 u minus 1 du. And I have now substituted everything. Now this thing here is a little complicated. It still has a multiplication in there, but this multiplication can be distributed, right? The problem with the integral that we started with also had a multiplication, but because of the square root sign, you can't distribute this multiplication, and so you're stuck if you're just trying to do simple algebra tricks. But here, after the substitution, it still has this multiplication, but now the square root has kind of shifted to the other part, and now we can distribute it. So how are we going to distribute? You add the exponents. I get integral u to the 1/2 times u is u to the 3/2 minus u to the 1/2. And now we can do the integral just part by part, each piece. So this is going to say 1 over 5/2 u to the 5/2 minus 1 over 3/2 u to the 3/2 plus c. And then, as always, my last step is to replace the x's for the u's. And to refresh my memory, u was x plus 1. So my final answer, 2/5 x plus 1 to the 5/2 minus 2/3 x plus 1 to the 3/2 plus c. There we go. All right. So this was one in which you had to do a slightly weird, just one part of the substitution was a little weird, using the u on both pieces. All right. What do we got for time here? We got 10 more minutes. I had some that I wanted you guys to try. Maybe I'll give you a couple moments I had 3. I don't know if 10 minutes is enough to do 3 different ones, but we'll see what we can do. I just give it to them. How about first one? Integral 0 to root pi of x sine of x squared dx. That's a fairly straightforward one, and then this one is a weird one which requires a tricky little step. If all those other ones were too easy for you. All right. So how about let's take 5 minutes or so, work on those, and then we'll go over them. If we were in person, I would walk around and try and help you out, but you get nothing. Sorry. I don't know how to walk around. All right, we only have 5 minutes left, so I think we should go over these. It's all right if you haven't quite finished them both. And the second one is a little tricky. Let's try the first one first. You know, for both of these, you got to do the substitution. What'd you pick for the u for this one?
I said x squared on this one.
X squared is a good idea. That means the du is 2x dx. And hopefully you divided the constant here to make it 1/2 du equals x dx. Right? And then when I plug this stuff in here, I get... So I'm going to ignore the boundary values for now. I'm going to plug them in at the very end. But this is x and then sine of u and then dx, right? I just stuck stick the u where it goes. And then if you want to gather things together, I put the u stuff first, and then what's left over is x dx. And lucky for me, the x dx here matches the x dx up here, which is the 1/2 du. So this becomes integral sine u times 1/2 du. I pull the 1/2 out. And then the substitution is done. We're ready to do the integral. I hope that's what you got. Any questions about that so far? All right, what do we get for the antiderivative? What do you say? Anybody know how to keep straight the minuses?
2 sine to the 1/2. Or I'm sorry.
No.
I'm sorry. 1/2 sine to this squared. I don't know why I said that.
Yeah, you don't have to do any squaring or anything like that. This is just the integral of sine.
So it's cosine, right?
Yeah, it is a negative cosine. The derivative of sine is cosine. The integral of sine is negative cosine. So what I end up with is negative 1/2 cosine u. That's the integral of sine u is cosine u. Ordinarily, you'd put the plus c here, but in this case, I'm not going to because I have a definite integral. I got numbers to plug in eventually, but first I'm going to put the x back in. And then I plug the numbers, 0 and square root of pi. You may have thought the square root of pi was a weird number to plug in, but it's not so weird because you end up squaring it inside there, right? Anyway, my answer is -1/2 cosine of root pi squared, and then subtract -1/2 cosine of root pi, no, 0 squared, which is just 0. Right? And that, you could leave it like that if I didn't tell you to simplify. Probably I would tell you to simplify the cosines at least. Anyone remember what's a cosine of 0? You can show me the fingers if you want. I saw someone. It's 1. Yeah, so this is, whoa, sorry. This part is going to be just plus 1/2 at the end, right? Because that cosine of 0 is 1. Cosine of root pi squared. Root pi squared, of course, is pi. And cosine of pi is, what do you say?
-1.
Yeah, -1. So this is going to be -1/2 times -1. That's another half. So actually you get 1. That's your final answer, right? That's cute. No one was expecting 1 as the answer, right? Okay, let's. Any questions about that one? This is the less hard one. The other one is the harder one. Can I? I'll do one of these. What? Not that. I'll do that. I do that. Yeah. Come on. Okay. Did anybody make this happen? What did you choose for the u?
X squared.
Plus 1.
X squared plus 1. Yeah, that's the reasonable choice for the u as the inside of something. Then the du is 2x dx. And I'm going to divide the 2 like I always do. 1/2 du equals x times dx. So when I do this substitution, or when I start plugging in, I have x cubed times u to the 10 dx. You can slide things around like I usually do. U to the 10 times x cubed dx. And now is when you got to think about some fancy tricks here. Anybody, did anybody work this out? How do you handle x cubed there? It does not match with the du, which would be just 1x there. This is one of those ones that we did a few moments ago where you have to kind of match it with the u instead of the du.
Yeah, I was gonna say, can't you multiply it to like the third? Like, can't you multiply like the exponent out or whatever?
This? Make it like du to the third?
Yeah.
Yeah, that is not gonna work. The du or the dx or whatever inside of an integral is not allowed to be. You can't have like dx squared because that messes up the integral. You won't be able to find the antiderivative of such a thing. Like this, you know, if you have integral of x squared dx, you can do that. That's 1/3 x cubed. Integral of x dx squared, that's like, that doesn't even mean anything. So you can't modify the dx or the du in that way. Any other ideas?
Could you take out the 1/2 when you substitute 1/2 to u and then raise that to the third? Is that allowed? So it would be 1/8 on the outside.
No, because like you can't just. I feel like you're saying instead of cubing the entire thing on both sides, I'm only going to cube this and only going to cube this, but that you can't do that in an equation. You gotta, if you're going to do the same thing on both sides of the equation, you got to do it to everybody. All right. We're out of time, actually. Maybe we'll just start off the beginning next time with this one, because it's a little tricky, and I don't want to squeeze it into, you know, -2 minutes. So let's leave it at that. We'll start off next time with that one. All right. Hope you all have a good day. You can go back to bed if you want, or whatever else you're doing. All right. See you on Friday.